In our last video, we found out that the tangent plane to a level surface is a plane passing through P naught, where P naught is a point on that level surface that is normal to my gradient vector. Thinking about how we found planes earlier in the semester, well, if I have a vector perpendicular to my plane, then this is our component equation of that plane. So in this video, what I'd like to do is find the plane tangent to z equals x squared minus y squared, our hyperbolic paraboloid at the point 2, 1, which would be about right there in the first octant. And then I'd like to find the tangent plane to x squared plus 2xy minus y squared plus z squared equals 7 at the point p naught equals 1 minus 1, 3. So I have two different situations here, because this is defined as a level surface to a function on 3 variables, but this is defined as a function on 2 variables, just a regular surface. I could think of this as a little f of xy equals x squared minus y squared. Well, my solution to this first problem will involve just rewriting it, because every surface, every function on 2 variables, is really a level curve of a function on 3 variables if I just take z away from both sides. In our last video, we saw a special case of this where we rewrite this formula with a minus 1, where the partial of z goes. I always prefer just to think about this as one process and rewrite any surface, like the one I'm given here, as a function on 3 variables equal to 0. So let's go on and see if we can find the tangent plane in number 1. So I'm looking for the plane tangent to z equals x squared minus y squared at 2, 1. So my first job is to reimagine this as a level surface to a function on 3 variables. And since this is a function on 2 variables that maybe I was thinking of as little f, I'll call this big F of x, y, z, though it doesn't really matter what you call your function. So I'll take the partials and write my gradient vector down. So partial with respect to x is 2x, partial with respect to y is minus 2y, and that last partial minus 1. Okay, so now I need to evaluate this at a point. And this is a function on 3 variables, even though this doesn't really call for z. In a moment, I'm definitely going to need to know the value of z to be able to write that expression down. So let's go on and find z. So the point I'm dealing with here is the point 2, 1, 3. That's my p naught. All right, so now I can evaluate del f at the point 2, 1, 3 to find the vector perpendicular to my surface at the point 2, 1 in its domain. Well, just evaluating, I get this vector, 4 minus 2 minus 1. So now I'm ready to write down my plane. And as I typically would for planes, I want to rewrite this in the simplified format. And so my final answer, my tangent plane is the plane 4x minus 2y minus 1z is equal to, let's see, 8 minus 5 is 3. Now also remember, I could hop straight down to this last step by remembering that my tangent plane is ax plus by plus cz equals d. A, b, and c came from my perpendicular vectors, so they come from my gradient. And then d was formed by taking the dot product of our normal vector with a vector that was the position vector of that point, which I'll just call vector p here. So for us, that would be our gradient, 4 minus 2 minus 1, dot product with the vector pointing at P naught, 2, 1, 3. Well, 4 times 2 is 8, minus 2, minus 3, and we could hop straight down to this last simplified equation for our tangent plane. Okay, so our second problem gave us a function, gave us a surface defined as a level surface to a function on 3 variables. And I like to always write that down first. The function I'm dealing with here is x squared plus 2xy minus y squared plus z squared is equal to 7. It doesn't really matter what this is equal to as long as it's a level surface. It would change the shape of the graph, but it's not going to affect my gradient. And in fact, you could imagine going on and taking 7 away and dealing with the level surface where all of this was equal to 0. We'd have the same graph because we've just taken 7 away from both sides of the equation, and the gradient wouldn't be affected either because the derivative of a constant is 0. All right, so del F this time. A partial with respect to x would be 2x plus 2y. Partial with respect to y would be 2x minus 2y. And then finally, a partial with respect to z would be 2z. I need to evaluate that at my point. So let's see, I'll get 0 out in the x coordinate, and then I have 2x plus 2x minus 2y. When I plug in 1 and minus 1, 2 plus 2 is 4, and then finally 6. All right, this time I'm gonna go on and find that constant on the other side by taking a dot product of the vector that I know is perpendicular to the plane I'm looking for with the vector that points at the point I was given. So let's see, 0 plus a minus 4 plus 18. My plane will be equal to 14, and I have 0 x's, which I wouldn't usually write down, but I feel like it right now, plus 4y plus 6z equals 14. And I don't want to leave my plane written down like this with all these even numbers in it. If I can divide out a constant, I might as well. So my final answer will be 2y plus 3z is equal to 7. Since my gradient vector is a multiple of this vector, I could have gone on and simplified it and hopped straight to this answer.